Welcome back to the second part of this contrastive learning tutorial. Today we will implement such a framework for point cloud data using PyTorch. As always, I've prepared a simple Colab notebook which you can use to experiment. Before we however begin with the implementation, I need to fix some mistakes I made in the last video regarding the normalized temperature scaled cross entropy loss. First of all, I was made aware of the fact that I accidentally didn't include the temperature in the exponential term of this formula. Instead, I put it outside of the exponential term. Just as a refresher, this hyperparameter balances the effect of the similarity measures and therefore also the compactness in the embedding space. That's mainly because the similarity measures are bounded, and with this additional parameter we can determine how peaked the distribution is. It has been studied extensively, and it's common to choose a small value like 0.1 or 0.2. Talking about bounded similarity measures, I also said that the range of cosine similarity is between 0 and 1, which is of course not true. This metric is used to measure the angle between two vectors and is in the range of -1 to 1. I think I confused this because the exponential term in the formula enforces positivity anyways. Finally, the denominator does not only include the negative samples as I stated, but instead the negative and positive ones. The only index that is excluded by this indicator function is I, because that would lead to comparing the embedding with itself. Alright, that should be it. Thanks to everyone for pointing out these mistakes. Now let's have a look at the data for this implementation part. Alright, so this is the Colab notebook and we will use a library called PyTorch Geometric, which most of you probably are familiar with. And we will use it because for point clouds they have support for a couple of layer types, but we will talk more about this in a second. I install Conda on Colab because somehow the installation of Torch Geometric is slower when only using pip. That's why you first have to run these two cells, and after that you will need to restart the runtime and run it again, and then it will be set up. In order to restart it, you can go down here, press this button, and it will automatically restart it for you. Also make sure that you select a runtime with a GPU accelerator such that the model trains faster. And then when we run this again, everything should be fine. So the next step is taking a look at the dataset. We will use a dataset called ShapeNet here that consists of many different point clouds of shapes, and we will only use a small subset of them consisting of these 4 objects: table, lamp, guitar, and motorbike. And also because of RAM restrictions, I will only select 5,000 data points, otherwise it won't work on Colab with the training later. I can get the dataset from Torch Geometric datasets, and when we have a look at the first sample, we see that we have a couple of attributes: X, Y, position, and category. And as we do self-supervised learning here, we will just ignore the category and also Y. We just assume we have no labels at all. So the only information we have given is X and the position. And the position is the normalized 3D position, so 3D coordinates, X, Y, and Z. That's why we have 3 values. And X are the normal vectors. This can be used as additional features, but we won't use it in this tutorial. And here's an example of how the position matrix looks like. For each point in our data set or in our data points, we have these 3 coordinates and they're normalized, I think, between -1 and 1. Of course, this tutorial is also applicable on other data modalities. It's just that I used something different here, which are point clouds, but of course you can use it also for audio, for vision, whatever you like. The basic idea always stays the same. Alright, now we can use Plotly to plot this 3D shape. Here I have a function called plot 3D shape, and it will take the 3 coordinates and create a scatter plot out of them. Here I can select the index I want to investigate. So this is a table, I guess. And let's have a look at another one. Okay, this seems to be a motorbike. And here I can also check the distribution. So it looks like we have mostly tables, but also some lamps, guitars, and other stuff. And here you can see the number of points this point cloud consists of. Of course, if you want to use less, you can also sample a subset of the points, and this will look like shown on this image. Alright, that's it about the dataset, and the next step will be the data preparation. Before we move on with the code, let's talk a bit about augmentations. In the paper SimClear, the authors generate two views of an image. That means they don't use the original data point at all, but instead attract and repel the representations of only augmented images. I didn't find a particular reason for why it's done like that, but I assume that it adds some more variance to the training and avoids that the model only learns how an image was augmented. It is important to mention that augmentations have a very big impact on what representations are learned. That's why you can also say that they introduce a bias. For example, if you only randomly crop the images and don't change the color at all, it might happen that the only features that are learned by the model are which color the background has, because dogs often stand on green grass. Similarly, it can also happen that you create augmentations that can't be properly distinguished by the model. Regarding this, I can also recommend an ICLR paper from 2021, which talks about the inductive bias of augmentations. Now for point cloud data, I didn't really find any best practices, and therefore I came up with some very simple augmentations for this tutorial. Let's have a look at the code. I also want to mention that typically you calculate the augmentations on the fly, so simply in the forward function of your model. But it can also happen that you need to pre-compute them because you have heavy computations, for example. If you use PyTorch geometric for that, you can also store multiple data points like a positive and negative sample in one data object, which makes it convenient for batching and things like that. Here, however, we will calculate the augmentations on the fly, and we need two augmentations for each data point. And the question is, of course, what are good augmentations for point clouds? For example, rotation is problematic because depending on the layer you use, some of the layers might be rotation invariant, so this augmentation won't have any effect. But there are also other augmentations like jittering or shifting the point clouds. So let's have a look at some of those. And for this, I will use PyTorch Geometric's Transforms module, which fortunately already has some of these augmentations implemented. And actually, you can even apply them to a whole batch, which is very convenient because otherwise you would need to calculate it separately for each point cloud in the batch. And here I apply random jittering. That basically means you add some noise, and you can also play around with the parameters I used here. Then I randomly flip the point clouds, and then I do some shearing, which means like a shift in one dimension. All right, let's have a look at some examples for these augmentations. So this randomly selects some data point from the dataset, and in this case we get, I guess, a table, and the augmented version of that table looks like this. Okay, so you see it's shifted a bit, and we have more noise around the object, but still it's similar to this original data point. Let's have a look at another sample. So the original data point is, okay, another table. And here, okay, you see it's shifted in one dimension. Yeah, so let's have a look at one more. But you can still identify the original data point, which is important because the model will also need to be able to distinguish data points. And now what we will do is we will use two separate augmentations of this object, and the model needs to tell us, okay, those belong together and form a positive pair. The next part is the model building. For this, we first have to think about how we can process point clouds with machine learning models. Point clouds are simply a collection of points in the three-dimensional space that represent an object. For example, a table like in our dataset. Some special properties about this form of data are that the input size is dynamic, meaning each object usually has a different number of points, and also the density in this space can be very irregular, as some areas have many neighbors and others don't. Where do point clouds come from, you may ask? Often they originate from 3D laser scanners such as LiDAR scanners. That's why they, for example, also often occur in autonomous driving applications. There are plenty of ways to process these point clouds for machine learning purposes. To give you an idea about this, I've picked out 4 popular approaches. One thing that you can do is place your object on a 3D grid and thereby introduce a natural order to your set of points. In a 2D space, a single cell is called pixel. In a 3D space, it's a voxel. This allows us to apply 3D convolutional neural networks by simply sliding kernels over the 3D grid. As you can imagine, this is not the most efficient approach because this representation is very sparse, which means there is lots of unused space that is usually 0. Another approach is to look at the object from different angles and take the 2D snapshots as input for a regular CNN. This approach is more efficient, but the downside is that we don't really use the 3D information. Besides that, there exist lots of handcrafted descriptors, for example, calculating histograms over the spatial distribution. This works by summing up the count of all data points in predefined bins along one axis. Just like in the previous example, these features are just a simplification of the input and can sometimes be limited regarding expressiveness. Finally, there are different deep learning models that can operate directly on the point cloud itself. Point clouds are invariant to permutations of their indices. These networks therefore need to be permutation invariant, which means the ordering of the inputs is irrelevant to the model. If you're familiar with graph neural networks, you will see many parallels later. In my implementation, I will make use of methods belonging to the last category, and therefore let's investigate it a little bit further. Each of the points of our point cloud is described by 3 coordinates, x, y, and z. Typically, there is no topological information, meaning that we don't have an underlying graph or anything like that. So basically, all we have are many of these triplets. How do we input this into a neural network? Remember that we need to be able to handle arbitrary permutations, so the model shouldn't care about the position of each point in the input matrix. One of the first approaches that operated on the point clouds directly is called PointNet, published in 2017. On a high level, their model does the following. All of the points are passed through a shared multi-layer perceptron that transforms the coordinates into vectors of size 64. For visualization purposes, I changed it to a dimension of 4 here. After that, the transformed points go through another dense network and are converted to a dimension of 1024. Here again, I simplified it to 6. So pretty straightforward so far. Now the permutation invariant component comes into play, which is max pooling. For each dimension in the final vector, the maximum is selected and combined into a final global vector. This operation is independent of the order of the points. This final vector is the global fixed size representation of the point clouds. The authors then use the local vectors after the first transformation and this global vector after the second transformation together as features for downstream tasks like classification or segmentation. One downside of PointNet is that there is no aggregation between local points and only the global max pooling in the end, which is applied on every single point in the object. PointNet++ is an extension of this model and works as follows. The main idea is to aggregate in a hierarchy instead of one max pooling at the end. It's a bit like having a growing receptive field in CNNs. The method begins with an algorithm called farthest point sampling to choose a subset of starting points. Then local areas around these centroids are selected and used to build groups of points. After that, the points go through a multi-layer perceptron transformation and are finally pooled according to their group membership. So all transformed points that belong to one cluster are combined into one vector. This leads to building local representations, and after repeating several of these blocks, we end up with global representations for the whole object. The authors present different strategies for this approach, but I won't go further into detail here. This method has many parallels with graph neural networks, especially the local aggregation and the permutation invariant pooling. The third model I want to talk about here is called EdgeConv. The motivation is quite similar to PointNet++, meaning that this model also wants to capture better local features. It starts by collecting the k nearest neighbors around each point. For example, here the yellow coordinates represent the central point and the gray ones the neighbors. The choice of k So the number of neighbors depends on the size of the point cloud. For simplicity, we assume k equals 2 here. We also add self loops, which makes the central point also a neighbor. Then it takes both the center point and each of the neighbors as input for a fully connected neural network. The outputs are edge features between the nodes. That's why it's also called EdgeConv, as the convolution happens on the edges. On those edge features, a permutation invariant function like max pooling is applied, and this representation finally describes the relationship between the center point and its neighborhood. There is also a comparison with other approaches in the paper like graph neural networks, in case you look for more details. According to the paper, this approach outperformed PointNet and PointNet++, and in addition is significantly faster. Therefore, we will also use it in our implementation. Besides these methods, you can find plenty of others, such as the point transformer or the SE3 transformer, which are also worth a read. Alright, now that we know how we can handle point clouds, let's quickly have a look at the overall model architecture we want to build. This overall setup is nicely visualized in this plot from the below referenced survey. We first generate different views of our data, then pass them through the model to get representations, and finally apply a projection head that squeezes the representation into a smaller dimension to apply the contrastive loss functions. For the encoder, we will simply use the EdgeConv layer that I just talked about, and the projection head is a fully connected network. When I saw this, there popped up some questions in my head. First of all, why do we need a projection head? This was discussed in the follow-up work of SimClear called SimClear v2. We want to apply the loss on a lower dimension, which we can see as a compressed version of our representation. That's because most similarity measures that are used in contrastive losses suffer from the curse of dimensionality. Therefore, when we calculate the loss on smaller vectors, we will get better results. The second embedding space is sometimes also called the metric embedding space. Later at inference time, we simply drop this projection head and fine-tune on downstream tasks with the original representations directly. Enough about the theory, let's go back into the notebook and implement this. So this is the implementation for the model. It's pretty simple. First, we have two of these dynamic EdgeConv layers, which I just talked about. K is set to 20 here. That means we aggregate on neighborhoods of the size 20. Of course, this is a hyperparameter, so you might want to do some fine-tuning here. And then we have the max pooling at the end of each of these layers, which aggregates the local information. We have two of these layers, and then inspired by this example, the output of each of these layers is combined again. So this outputs a size of 64 and this 128. And those two go into another linear layer. And then this is the joint representation of these two feature extraction layers. As mentioned before, K, so the K nearest neighbor sampling, depends on how big your point clouds are. So 20 is relatively small, I would say, if we have like 2000 points. So it might make sense to use a larger number like 100 here. But again, you have to try this out. And then what I added here is this projection head that compresses this output representation into a smaller dimension of size 32. And this will be the compact representation that goes into our loss function. Then we already have the forward function. And here, first of all, I have an if-else statement. If we train, we of course want to apply augmentations. If we test, however, we don't want to apply augmentations and want to convert the original data point into a hidden representation. So in case of training, we augment the data 2 times, which is called augment 1 and augment 2. And then we extract the batch features or the batch index and the positions, which are our features, you could say here. And then we go through these 2 convolutions, and then we go through this linear layer, which is this combined linear layer. And then the same thing for the second augmentation. Of course, an improvement of this would be that you stack those 2 augmented pairs together and just do 1 pass through the model, but I didn't add it here, but this could be an improvement to speed up the training. And then in the end, we just apply the global max pooling, and this gives us the global representation for the whole object. And then down here we have compact H1 and compact H2, which applies this projection heads and gives us like the compact representations of those original representations. Now we can already talk about the training. So for the training, as I said, we use anti-accent loss or anti-cross entropy loss, and we choose a temperature of 0.1. And I take this loss from a package called PyTorch metric learning, which includes many of these metric losses. And by the way, this loss is also called info NCE sometimes. Then just some standard codes, like we put the model to the GPU, we choose an Atom optimizer with some initial learning rate, and we also have a learning rate scheduler. Then we have a data loader, and unfortunately I can't choose a larger batch size on Colab because I run out of RAM. So on Colab you typically have around 12 gigabytes of RAM, and this brings us to an important point about contrastive learning, which is the batch size. Let's have a look at this plot from SimClear. As you can see, the batch sizes for contrastive learning are typically very large, and higher numbers tend to produce better results. That's because you have many more negative samples within a batch. For example, for size 1024, you have 1022 negative samples and 2 samples that belong together and form a positive pair. And of course, the more data points the model contrasts against, the more compact the embedding space will be. Certainly, you will have more false negatives as well in the case of self-supervised contrastive learning, but as mentioned in the first video, there are also approaches for better selection of negative samples. Anyways, typically the batch sizes should be very large. In this case on Colab, I could only choose 32, but still got decent results with it. Alright, so now let's train that model. And for this, I only have a very simple train function here. We don't really need a test function because the testing usually happens on downstream tasks. And the way how this works is that we iterate over the data loader and then pass the data through our model and get these 4 representations. The first one form a positive pair for the first and second augmentation, and then the same for these compact representations that go into our loss. And now, in order to put that into our loss, we need to do some preparations, or we need to tell the loss which parts belong together. So this is a quick example on images, how it works with the indexing for this loss function. We augment each image in our batch with random transformations, such that we end up with 2 sets of augmentations. We pass those either separately or ideally as a stacked batch through our model and get the output representations. Now, in order to tell the loss function which images belong together, we use this index vector. All embedding vectors with the same number belong together and form a positive pair, and all other ones just form negative pairs. And that is exactly what's happening here. So I first concatenate these 2 embeddings, which are the first and the second augmentations. And then what I do here is I have a thing called labels. And for that, I simply increment from 0 to the size of the embedding, like 1, 2, 3, 4, and so on. And then I concatenate that 2 times, just like on the plot I've just shown. And this tells the model, okay, the first one of each of these vectors belong together and the second one, and so on. And then we can pass the final embeddings, which are those 2 concatenated ones, plus the labels into the loss function. And then this gives us the loss. All right, and I just trained it for 3 epochs here. You can see the loss is going down. And this is the loss after the 3rd epoch. Now it's time to test our embeddings. And luckily we have labels, so we can visualize how the embedding space looks like. Of course, usually you don't have labels, so you need to fine-tune on downstream tasks or do some clustering. But in this case, we can actually check how good the embeddings are and how close together they are in the embedding space. All right, so we get 1 batch of our data set, which means 32 points. And we pass these points through the model and we give it the argument train false. That means we don't apply any augmentations. And in addition to that, we also get the labels. As I said, luckily we have them, so we can visualize the data in the embedding space. And now t-SNE is like a dimensionality reduction technique, and we reduce our final embeddings to a size of 2 such that we can plot it on this 2D plot. And for that I use seaborn scatter plots, and with this function I also label each of the points in this plot. So let's have a look. For one batch we get these embeddings. So we see the tables form a cluster, and also class 1 forms more or less a cluster, and we have one single green data point. So let's do this again. Maybe we get some clearer separations. Okay, here it's a bit better. So we see all the tables are in this area. Class 1 is in this area. Actually, those one are red, I think. And we have many green points that belong together. So what we can do now is we can select an index, say for example 11, and 11 is close to 31. So here I calculate the similarity between embeddings, and if I select now this index 11, it should tell me, okay, the most similar data point to 11 is 31, which is exactly what we see here. And what we can do now is we can visualize 11. Okay, we see this is a very simple table, and we can also visualize 31 now. And those should be quite similar, and in fact they are. So now let's choose another one. For example 12, for 12 the closest data point is 22. So when we run this, it should tell us, okay, 12, it's 22. And now let's visualize 12. 12 is, okay, this is a motorbike, and 22 is also a motorbike. All right, there you have it. We successfully learned meaningful representations of point clouds without labels. I hope you enjoyed this short tutorial and would be happy to see you soon in the next video.